Chapter 9, Alcohols, Class Life Sciences. Part 3, Chemical Reactions of Alcohol. At the end of this session, students should be able to define mild oxidation, identify the different types of mild oxidation of alcohols, write the equation of esterification of alcohol. Then part 7 of chapter 9, Chemical Reactions. The reactivity of alcohol is due to the hydroxyl group OH, which is the functional group of alcohol. In this chapter, we will study two types of reactions with alcohol: mild oxidation, and the second is esterification. First, mild oxidation. What is a mild oxidation? Mild oxidation is a reaction which takes place without breaking the carbon chain and occurs on the functional carbon. That means what? That means during the mild oxidation, the hydroxyl group with the functional carbon of the alcohol is converted into carbonyl group or carboxyl group according to the class of the alcohol and the conditions of the reaction. We will see that later. Then, if we make the oxidation of an alcohol formed of 4 carbon atoms, the organic compound obtained remains formed of 4 carbon atoms, because in mild oxidation we have same carbon chain. We obtain same carbon chain. We keep the carbon chain without breaking of the carbon chain. But the change takes place only on the functional carbon. There are 3 types of mild oxidation. First, catalytic oxidation. Second, catalytic dehydrogenation. Third, oxidation by an oxidant in an acidic medium. Now, catalytic oxidation. In catalytic mild oxidation, alcohols are oxidized by oxygen gas in presence of Cu as catalyst. It is called catalytic because it takes place in presence of a catalyst, which is Cu, and the oxidant is O2, the oxygen gas. This is the setup of oxidation. This is the alcohol, and this is the copper wire, which plays the role of catalyst. The reaction is exothermic. It releases heat so that the copper wire becomes red. The copper wire, which is the catalyst, becomes red hot due to the released heat. Since the reaction is exothermic, then we have release of heat, which makes the copper wire red. This process is called flameless lamp. It looks like a lamp in dark. This video shows the oxidation, catalytic oxidation of ethanol in presence of copper as catalyst. Flameless lamp experiment. First, we heat the copper wire. When it becomes hot, we put it in the flask containing alcohol, and the vapor of alcohol undergoes oxidation when it's in contact with the copper wire. The increase in the intensity of indicates that there is oxidation of the alcohol. This experiment shows the catalytic oxidation of alcohol. This experiment is called flameless lamp because it seems like a lamp. This video also showed the same experiment. First, we heat the copper wire. When it becomes red, we put the copper wire in another mirror containing alcohol. The vapor of alcohol undergoes oxidation. The heat released during this reaction, which is exothermic, makes the copper wire red. Now, catalytic oxidation of a case of primary alcohol. In case of primary alcohol, we have two cases. When the alcohol is in excess, which is controlled mild oxidation. The catalytic oxidation of primary alcohol, when the alcohol in excess, leads to analdehyde. Primary alcohol in excess plus O2, the oxidant is O2 in presence of Cu as catalyst, we obtain aldehyde. The general equation RCH2OH is the formula of the primary alcohol plus O2. We transform the functional carbon into aldehyde carbonyl group. That means the family is aldehyde, C double bond O, H. We, in neutral medium, hydrogen is balanced by H2O. We have in this in reactants 2 plus 1, 3 hydrogen. In product we have 1 hydrogen, then we add H2O to have 3 hydrogen in product to balance hydrogen atoms. Now we have 1 oxygen and 1 oxygen, 2 oxygen product. In reactant we have 1 oxygen in alcohol. We need 1 more oxygen, so that we multiply O2 by half to have another oxygen atom, to have 2 oxygen atoms in the reactant. This is the balanced equation of the reaction. Example, CH3CH2OH plus O2. We transform the functional carbon to C double bond O single bond H, and R remains the same, CH3. Then we obtain CH3 C double bond OH. We balance the hydrogen atoms, 3, 2, 5, 6 hydrogen in the reactant. We have 3 and 1, 4 hydrogen product. We add H2O. Now we have 6 hydrogen product. We have 2 oxygen atoms in the product. In the reactant we have 1. We multiply O2 by half to have 2 oxygen in the reactant, and the equation becomes balanced. Now, when oxygen is in excess, which is continuous mild oxidation, the catalytic oxidation of primary alcohol when the oxygen is in excess leads to a carboxylic acid. In fact, how can we know if an organic compound, oxygenated organic compound, may undergo mild oxidation or not? If the functional carbon, in case of alcohol, the carbon holding the hydroxyl group, if this carbon is hydrogenated, that means it's bonded to a hydrogen atom, then it undergoes mild oxidation. In case of primary alcohols, the alcohol undergoes mild oxidation. Secondary alcohol also can undergo mild oxidation, since the functional carbon is hydrogenated. The tertiary alcohol, the functional carbon in tertiary alcohol is not hydrogenated. This carbon has no hydrogen atom bonded to hydrogen atom. Then it cannot undergo mild oxidation. In case of aldehydes may undergo mild oxidation because the functional carbon is hydrogenated. In case of ketones cannot make mild oxidation because the functional carbon is not hydrogenated. Same for carboxylic acid. The functional carbon is not hydrogenated, then the carboxylic acid cannot undergo mild oxidation. Then only primary alcohol, secondary alcohol, and aldehydes may undergo catalytic or mild oxidation, all types of mild oxidation, unless dehydrogenation for aldehyde. Okay, the primary alcohol, first it undergoes oxidation into aldehyde. But when we have oxygen in excess, then the remained oxygen gas oxidize the obtained aldehyde into carboxylic acid. Then if we start from primary alcohol, we end with carboxylic acid. If the oxygen is in excess. Then to memorize, the catalytic oxidation of primary alcohol when the oxygen or the oxidant is in excess leads to a carboxylic acid. Primary alcohol plus O2 in excess give carboxylic acid. RCH2OH is the primary alcohol plus O2 the oxidant give RCOH. We balance the hydrogen, 2 and 1, 3 hydrogen. Here in product we have 1 hydrogen, so that we add H2O to have 3 hydrogen as in reactant. Oxygen in product you have 2 oxygen in acid and 1 oxygen in water, 3 oxygen. In reactants we have 1 oxygen and O2, 2 oxygen, then 3 oxygen. Then we need 1 O2. Example: CH3, CH, CH3, CH2OH plus O2. This is the functional carbon. We transform it into a carboxyl group. The R alkyl group remains the same. We obtain CH3, CH, CH3 this is R, that remains the same. We transform the CH2OH into COOH. Now we balance. We have 3, 6, 7, 9, 10 hydrogen in reactant. We have 3, 6, 7, 8. We need 2 oxygen, 2 hydrogen. We add H2O. Now we have 2, 3 oxygen. Here we have in reactant 1 and O2, 3 oxygen. This is the catalytic oxidation of primary alcohol. Now of secondary alcohol. The catalytic oxidation of a secondary alcohol leads always to a ketone. Secondary alcohol plus O2 give ketone RCHOH R prime. This is the primary alcohol, secondary alcohol plus O2. We transform the functional carbon with OH into carbonyl group, C double bond O, R and R prime remains the same. Plus we balance, we have 2 hydrogen here in product, we have no hydrogen. We add H2O to balance the hydrogen. Now we have 2 oxygen in product. In reaction we have 1 oxygen, we multiply O2 by half to have another oxygen atom to have 2 oxygen in reaction. Example: CH3, CH2, CHOH, CH3 plus O2. This is the functional carbon and the hydroxyl group are transformed into carbonyl group, C double bond O. R and R prime remains the same. We obtain CH3, CH2, this is R, C double bond O, CH3, this R prime. And we balance, we have 3, 2, 5, 6, 7, 10 hydrogen, 3, 2, 7, 5, 3, 2, 5, and 3, 8. We need 2 hydrogen as H2O, and we have 2 oxygen one oxygen reactant, we multiply O2 by half and to have 2 oxygen in reactants. Now of a tertiary alcohol. Tertiary alcohols do not undergo catalytic oxidation since the functional carbon does not have hydrogen atoms. Then tertiary alcohol plus O2, no reaction. Now 7.1.2 catalytic dehydrogenation. In catalytic dehydrogenation, alcohols are oxidized in absence of oxygen gas and in presence of Cu as catalyst. Then dehydrogenation in absence of oxygen, catalytic oxidation in presence of oxygen. In the two cases, we use Cu as catalyst. This is the setup of dehydrogenation of ethanol, CH2OH, into aldehyde. The vapor of ethanol, when in contact with the copper powder as catalyst, it undergoes into aldehyde, oxidized into aldehyde. The reaction is endothermic, so that the copper wire, which plays the role of catalyst, or the copper powder, need continuous heating to about 300 degrees. The reaction needs heating since it is endothermic. Now of primary alcohol. The catalytic dehydrogenation of primary alcohol leads to an aldehyde. Primary alcohol, Cu heated to 300 degrees, give aldehyde plus H2. Dehydrogenation, that means elimination of H2. RCH2OH. RCH2OH is RCOH H. We eliminate the hydrogen from functional carbon, hydrogen from oxygen, and double bond is formed to have RC double bond or single bond H, that means aldehyde, plus H2 eliminated. Example CH3, CH2, CH2OH, 1 for panol, give CH3, CH2, C double bond O, single bond H, aldehyde plus H2. B of a secondary alcohol. The catalytic dehydrogenation of a secondary alcohol leads to ketone. Secondary alcohol heated to 300 degrees in presence of Cu give ketone plus H2. In general, R CHOH R prime, then H from the carbon and H from oxygen are eliminated as H2, and C double bond O carbon group is formed. Then we obtain a ketone RC double bond OR prime plus H2. Example, this is the primary alcohol. Example, CH3, CH2, CHOH, CH3. This is a secondary alcohol heated in presence of Cu to 300 degrees with the same R remains the same, CH3, CH2. CHOH are transformed to carbon group C double bond O, and the other R remains the same, CH3 plus H2. This is the example of catalytic dehydrogenation of secondary alcohol. C of a tertiary alcohol. Tertiary alcohol do not undergo catalytic dehydrogenation since the functional carbon does not have hydrogen atom. Then tertiary alcohol, Cu 300 degree, no reaction. This is the end of part 3, catalytic oxidation and catalytic dehydrogenation.